We started with example 2 last time in part 1. We're doing pumps, chapter 4. So just a quick review for what this problem is about. We have this pump here, and it's delivering, let's see what kind of, I believe it's water, unless if they mention the specific gravity, or doesn't matter in this problem. I don't think we need that. Okay, so we're delivering from here through the check valve, all these, the DCV, and it comes to the cap side of the piston right here. And then it pushes this load, which is 40,000 pounds. And then from the back side, it goes down back to the DCV and then back to the tank. The pressure drop here, since this section, we give it in negative. We'll mention how we can add that to the pressure of the pump. The pressure drop from the pump to the cap side is 75, and the track pressure, or the pressure in the back, which includes the pressure here and in the line, the loss in the DCV all the way back, was 50 psi. We calculated the volumetric displacement last time. So what basically we did, we calculated the actual flow rate Q, which is the velocity of the piston times the piston area. That was the theoretical, since that was the actual, since it's coming from something that we measure. Where is it? It's here. And then using the volumetric efficiency for the pump, because that would be the same actual flow delivered out by the pump. So we found the theoretical flow, and then from that equation, or from the definition for the theoretical flow, which is the displacement times the rotational speed divided by 231, or regardless, that's just a unit conversion coefficient, we found the displaced volume. Okay, next I need to find Next, we need to find the horsepower required to drive the pump. We also mentioned that last time. We didn't solve, but we discussed it, so we'll just dive into it. So we said we have two equations you can use, either the mechanical efficiency equation, which has the pressure needed by the pump times the flow rate. This would be the theoretical flow rate if you use the mechanical. If you use the overall, which is basically the overall, the mechanical times the volumetric efficiency, that flow rate becomes the actual. So delta P, or P for the pump, times Q actual over 1714, all that divided by Tn over 63,000, but Tn, that's the mechanical power needed by the shaft. Okay, so we're looking into this one. Regardless which one you use, you should get the same answer. I'm gonna follow I'll follow my notes. I think I should have both. Yeah, I have both, and I got the same answer. If you do some rounding, maybe you'll get slightly different answer, but if you use the same, that's basically what you're doing. You're multiplying the mechanical by the volumetric efficiency, which you have, and that's what you used actually to find the flip from theoretical to actual. It was just the volumetric efficiency, so we should get the same answer. So now the question, we have both efficiencies, the mechanical and the volumetric, so I can get the overall. If I need P shaft, then I will need the pressure needed by the
Mm.
pump. What is it equal to? Okay, so if we look here, the pump needs to usually overcome the elevation, the static elevation, frictional losses, and push the load. The way we did it in chapter one, or yeah, chapter one, the last example, we calculated actually the pressure all the way from here to anyone trying to say anything? No?
Oh, sorry.
Okay. So we need to find the pressure from the pump side all the way to the cab side. And then I need also to be able to push that load. I need to push the load and be able to push the oil back or the whatever fluid is there, push it back through the return line back to the tank. Now, these two pressures, they're already given to us. The pressure, actually, the three this time, because we also need to do the suction from here to here. So they already calculated that. If not, then we will use what we learned in the previous chapter, the friction loss in pipes and fittings and valves, DCVs, etc. Uh, Fortunately, we have those given to us. We have the 75 from the pump to the cap side, and then I have the back side. Probably they should say neglect frictions till now. We will learn actually in the coming chapter, the cylinders, how to calculate the frictional loss between the piston and the cylinder, which is right here. If it's not given, we'll see how we can calculate that. We need more givens to calculate it. But anyway, for now, we don't have that. So I'll need to have the pump to overcome this pressure and to be able to push this load and the return pressure. Now, what's the relation between P cap and P retract? Anyone recalls how we calculated that side? We said we don't do pressure balance, we actually do force balance, and that's basically coming from, so if that's the piston, I'm going to call this P cap, PC if you want, that's the cap side, and here I'll call it P retract, that's the piston. And of course we have the load here, it's pushing. Uh, we use Newton's second law. Basically, you're saying summation of forces in the X, it has to be balanced. So since that's the line of motion, so in the X equals MA, it's either not moving, so we need to balance it, or it's moving at constant velocity. They didn't say, they didn't give much. They're not saying it's accelerating, decelerating. So they just said the piston is moving at this speed, so we're going to assume it's constant. So that makes then the acceleration equal to zero, and this would be equal to zero. We already discussed this last time, and we used that equation. So what are the forces? I have F on the cab side minus F retract minus F friction. I'm going to put it and then remove it. I mean, just set it equal to zero minus F load because the retract is pushing this way. Load is also resisting the pump and the friction. Those would be equal to zero. Okay, so that's F for the pump. It has to overcome F from the retract. So that not the pump, that's just like on the cap side. It's pushing this way. All these three are resisting and they're pushing this way. Now, as I've mentioned, we don't have friction between the piston and cylinder. So we'll set this for now, we'll just neglect it. So to find F cap or in general P cap, I'm looking for the pressure, but I can just say P cap equals this pressure and the pressure by the load. We do force, and then from the force, I can find the pressure. So if we write it again here, FC, that's equal to F on the retract side plus F load. Or it said the friction is equal to zero. What's the relation between the force and pressure? We'll use Pascal's law. Pressure is force over area. So this would be P cap times area of the cap for the piston, which is just simply pi over 4 d piston square, and the retract area is AC minus the rod area. I don't know which one they gave us. Yeah, we have the diameter for the rod, so we will have to calculate the retract area, which is the annulus area on the right side of the piston. Okay, that's equal to P retract times the retract area, which is here. That would be pi over 4 d piston square minus d rod square plus F for the load. So I can find then P on the cab side. Okay, why we need that? Because I'm looking for P pump, and we'll come back to that. P for the pump as has to overcome, first it's P here, PC, P on the cab, plus delta P for the supply line, which is given, what is it, 75 or 70? 75, plus delta P for the return. Plus, we have also pressure drop in the suction line. Usually, actually, this is minus because it's that side, and that's why it's given in the minus sign. Okay. You can say just simply delta P for the pump is P2 minus P1. So P2 is all the supply. So that's what we see here, delta P, supply, return, and PC, minus P1, which is basically the suction line. So we have this is 75. We have the return, it's 50. And this one is minus 4. So we can have that. So my missing variable is on the cap side, and that's why we needed to do that balance there, because I can't add a pressure created by the load to be able to push it, or friction between piston and cylinder. Where these would happen, it's actually inside this equation. So therefore, if we calculate the areas, P cap pi over 4, the diameter, I believe it's 8 inches, and the rod is 4. So here it's 8 square, that's this area. And then P retract is simply the one that's calculated, that's 50. This was calculated from the back side of the piston all the way back. So that would be equal to this pressure here, that's 50. And we have pi over 4, 8 square minus 4 square. So that's here, D piston minus the rod. And then just make sure you match the units. So F load, it's in pounds, 40,000, right? 40,000. Yeah, 40,000 pound force. So here, this one is in PSI, so pound per square inch. And then the area is an inch square, so this would be in pound. The same here goes. This is an inch square, so I should get PC and PSI. Okay, we will calculate that. I should get almost 833 PSI for PC. Okay, this is exactly what we did in that last problem in chapter 1. We found the balance, we found P cap, and then we moved from the cap side, the pressure there, all the way back to the pump. The only new thing probably is this one. The suction is given to us because it was the pump here, and then we had all the lines aligned in front. But this one now is like sucking the fluid from the tank to the pump. So this would be 833 plus 75. Actually, we already included that. Sorry. It's right here, the return. Okay. minus minus 4. So it becomes plus 4. Okay, why I remove that? It's not here because the pump needs to push the oil from here to here and then also overcome this. But to overcome this, we already calculated that in my P cap. So 79 and 833. I didn't calculate that. I directly put it in my equation. 912 psi. Okay. Therefore, if I use the mechanical equation, that would be P for the pump times Q theoretical divided by 1714, and then P for the shaft, and that's what we're looking for. So P for the shaft, and that's in horsepower, is 912 psi. I don't need to write the units because I'm not gonna cancel anything. It's a mixed unit equation. Q theoretical, we calculated that last time. It was 42.6 gallons per minute, divided by 1714, and then only the mechanical efficiency, which is 0.9. So I got 25.18. Let me just double check. Yep, 25.19 or 18. I just put it as 25.2. If you do the overall, you should get the same equation, the same answer, sorry, because you're just playing between Q theoretical and Q actual, you're just switching those two. So this would be those two efficiencies and then the same equation. And here it would be Q actual and all that divided by 1714 times P input, which is P shaft. So if you plug here, what did we have here? That was the calculated one, 30, the measured 39.2 GPM. You will get the same answer, 25.2 horsepower. Which one should I use? Well, it's up to you, but just make sure if you use the overall efficiency that you're using the actual. If you're using the mechanical efficiency, you use the theoretical flow rate. All right, that's part two, the horsepower required to drive the shaft. The next part is we need to find the input torque to drive the pump. So the torque needed to drive the shaft we found. So now I'm just going to the same definition for my equation, which is Tn over 63. And that's actually the definition for P input. So now we found P input, it's for the shaft, it's 25.2. Okay, let's see. I need one more slide. So P shaft, it's T in inch pound times N in RPM over 63,025, and that's equal to 25.2. It has to be in horsepower to have the units. So Tn for the shaft is 63,025 times 25.2 horsepower divided by N. What was N? 1800? 1800, not 1,000. That's a lot. And this one would be equal to 882. 881.8, or you can just round it up. We're not going to use that in the next part, so it shouldn't make a big difference. Okay, and then in the last part, part D, what we need is the percentage of the input power that we use to drive the load. So what's the power used at the output to drive that load with respect to the input load that we're using or that we're drawing and to run the pump. This has a another name if you want. Anyone can guess what's that? The percentage of the input power used to drive the load. What would that be? Any guesses? So how much power I need to drive the load with respect to the power that I need to run the pump? What does that represent, that term? Am I muted? No, you're not speaking. This is actually called one last chance. One, two, three. This is the efficiency for my system, how efficient this whole cycle that you see. So we have efficiencies, you might argue. Well, I have the volumetric and mechanical efficiency right there. That's for the pump. Now I need to find, or they're asking us to find how much I'm using to drive the load with respect to the input. What's the difference between the two? That would be the loss. If I'm using all that, then that's a perfect system. You don't have any losses throughout the system. So that's actually the question could be, what's the efficiency, how efficient your system is, or this cycle? What's the efficiency of this cycle? So you have to differentiate between the pump and some other systems. Okay. So to find the percentage for my system, I need to find the power out from the whole system, not just the pump, over the power in used by the pump. We already calculated this. This was 25.2 horsepower. So now what's the power out from the system? That's the power delivered by the piston. And that's equal to F times V. I need that to be in horsepower just to match this 125.2 horsepower. So the force is 40,000 pounds. The velocity is 3 inch per second. So I'll divide by 12. That would be feet per second. The 1 horsepower is 550 feet per second. Okay, so I'll need to divide that by pound-foot feet. Like I'm missing something. That's just speed. Pound-foot per second. So that's exactly what we need. And I'll divide that by 550. Foot-pound per second per horsepower. So this whole thing will cancel. Foot-pound per second with foot-pound per second, and then the per horsepower will go up. So the final answer would be in horsepower. And I got 18.2 horsepower. So we'll plug it here. And if you want, you can leave it as a decimal or multiply it by 100, and that will give you the that percentage or the efficiency for your system, 72.2%.
So is the loss 30%?
Yeah, almost. Now, where's that loss? It could be not just the pressure drop, but you can calculate the power drop. You can actually see it in one of the, I think I said ignores. We'll talk about that when we assign the homework, which we're going to do probably today. So the loss is not the pressure drop, the loss due to pressure drop, which is one of them. Usually there are some other hidden losses, which are in terms of it's coming from friction, but it's dissipating as heat inside your system. So that's another. Maybe there's some leakage somewhere in the system. So if you try to equalize or check the pressure drop created throughout the whole system and find the loss from that, which we can easily do as a power, just multiply by gamma and convert that to horsepower. Maybe they wouldn't match between the input and the output. Hey, it's not matching. I only have delta P, where there are some other losses which you may not see. But basically, yes, there are. If you can find a system with no loss, okay, that would be perfect. Uh, okay, any other questions? Okay. The next part, we went over this, but we want to go a little into uh, P-compensated pumps and how we can use actually valves to aid in that control for how we can control the load due to a change in some other parameter. So we discussed this last chapter and actually the chapter before as well, which is flow. Usually we can control it and we can control the speed by using either if it's just a fixed displacement pump. So we need to do a just one-step reduction in the speed or the flow. I can use the orifice. If I need to adjust that flow from time to time, so basically I need a variable valve, and this is one example, the needle valve. You can close it, open it. So basically that's a variable output that I can get out of this. Okay, when do we need those? When you have variable or fixed displacement pump. We discussed this as well. We said if it's variable, the pump itself should adjust the speed, the rotational speed, so that you can control how much you're delivering out. So in most cases, you don't need that. I only need it with fixed displacement pump. Why? Because in fixed displacement pump somewhere, I don't have any cycle. Yeah. So in fixed displacement pump, the pump is, we'll go over the other, I just needed this cycle. The pump is delivering constant flow and pressure. And this flow is actually driving the piston. I need to control the speed. That's what this topic is about. Control the speed by controlling the flow. How to do that? I can't adjust the pump. So basically, I need a valve somewhere to be installed so that you can open it and close it. Of course, if you recall the pump, if you recall the valves, when you did valves, we said we have three different types of, three different categories or parameters for valves. You have direction, you have pressure drop, and we have the flow. You might be controlling one, but the other two would come with that, but you can't avoid it. Like if you want to close it in order for you to control the flow rate, to control the speed, it would create pressure drop, although you're not interested to have any pressure drop. And that's our actual discussion when we come to this slide. Like, where should I put this valve? Should I put it in the supply or the return line, and so on? Okay. If it's variable displacement, then the pump can, as we saw last time in that video, the load would send a signal to the pump, so it would adjust. We saw the piston pump, how it adjusts the swash plate, so it would control the output flow, and then it would control the speed as well. So in general, it's needed. You might still use it with variable for some other reasons, maybe pressure drop and so on. But in general, we need it with fixed displacement pumps, not variable. The variable are they come with what we call P-compensated pumps. Some valves are actually called P-compensated valves, which are instead of the pump. If the pump is not P-compensated, so it doesn't adjust, the valve itself can adjust, so you don't have to go manually adjust the setting. It can adjust itself, and that's actually the two coming slides before we hit that circuit that I was showing you. So as mentioned, if you control the flow, there will be some pressure drop. You can't avoid that, and energy losses. Okay, that's exactly what I was talking about. This is the P-compensated valves. Basically, it's a valve that adjusts the flow in order to give you a constant pressure at the output. First, the symbol, it's still variable, but it's automatic control or adjustable. If we look here, what do we have? I have this pivot or whatever thing, it moves up and down. We'll see how it moves. But if you look here, we have an orifice that would first forget about all the other parameters that we see. I have P1 here. I need to drop it down to P2. So I'm going to use this orifice. That orifice would give you the main pressure drop from P1 to P2. If you look into the blue from the back here, it's going to here, and there's a spring right there. So P2 and the spring should equalize P1. At that instant, this spool should remain balanced, so it's not going to move. Okay? So let's assume, I think I have some numbers. Let me see. So now if the load is going to change, or actually the case that we're going to see on the next slide, if P1 is going to change, then if that orifice provides us with a specific pressure drop, then P2 would increase. Well, we don't want P2 to increase. What's going to happen if P1 is increasing? What would happen in this system? If P1 increases and P2, we want to set that to be constant, then it would, if you look here to this portion, it's going to push up because now the balance is no longer valid. Actually, P1 is more than what the balance P1 is, and it starts pushing up because now it's above the force by P2 times the area and the force of the spring. So that spool moves up. What happens as it moves up? You see this corner. Now we start blocking some flow. Well, we're not interested in this specific example in the flow. We're interested in creating pressure drop. So the pressure would drop enough so that it comes back to whatever output I need here. So if we look into this example, so originally I have the supply pressure, 500, that's P1, PSI. I need to make this to give me an output of 100 PSI regardless. Okay. Then that orifice is actually providing me with 400 PSI and the spring as well. So first, this one is providing 400 PSI to give me the 100. So I'm going to buy one that provides that much. And also the spring would provide me with 400 PSI because it's balanced now. So I have 500. The pressure by the fluid, the blue one, is 100. So therefore, the spring is 400. Okay. Now let's assume that the pressure jumps, P1, the supply pressure, jumps to 600. Then if you look here, I have 600 pushing up times the area, of course. We're not calculating in general, but P1 now jumped to 600. I only have 400 by the spring and we're starting with 100, so it's not balanced. What happened? That spool starts moving up to drop this down to create a pressure drop of 100 psi. Okay, is that clear? So it's very similar to the P compensated, and that's why this is called P compensated uh, valve. The pump, it's P compensated pump. So a change in the load sent a signal and then adjusted the swatch plate inclination angle, and thus it adjusted the output flow. This is the same concept. Okay. The next topic that I would like to discuss is where should I install, in general, these valves, the needle valve, the P compensated valve, and so on. So if we have this circuit, and I need to remember, we're talking about how we can control the speed and the flow. So let's say we're trying to control the speed of this piston. Okay. So I need to restrict the flow. So I can install it here in the supply line. And this return will go back to the tank. I can actually put the valve here. This also controls the flow. So it's restricting this so that it gives me the required speed, or maybe I don't want to put it in either one, the supply or the return. I can put it there. So now I have an additional line. That's why it's called the bleed off circuit. So we're bleeding some of that. So if you have 10 GPM coming here, I'll just I only need 8 to control here. So I need to open this to allow 2 GPM. Okay. So which one should you go with? Which one do you think, if you're designing and you want to place a valve, should I put it in the spline, return, or the bleed off? So the question, the answer, it depends. Okay, because each one has its own advantage and disadvantage. So now we're trying to control the flow. But I said with the flow, it's not just free, you can control it and you're done. No, there will be pressure drop. So if we look into the first one here, that's the supply. It's coming and it pushes on the piston down. So now if we're trying to calculate the pushing load, how much I can push, what's F? It's P times the area of the piston. This is not going to change the area. We're not changing. Now, if I have the piston, the valve here, then the pressure is going to drop from whatever pressure it was here, or it was here before I put the needle valve. I have now some pressure drop due to that valve, so it's going to drop. That means the pushing load in the extension phase is reduced, or it's limited, right? If we look into what we call the meter out, because it's installed here, I didn't actually create any pressure drops in my system. Additional pressure drop, let's put it that way, because there is pressure drop in the lines, valves, etc. So this one, it's P times the area. It didn't change. Anyone can guess what would be like a disadvantage of putting this one here in the supply, in the return line back to the tank? From my talk and what I presented to you right now and this on this slide, what do you think a disadvantage if we go with the meter out?
It will slow down the retraction.
It would slow down the retraction. So now if I need, so again, it depends on the application. If you're pushing, let's say this cycle is just pushing boxes, so it goes empty in the retract. Well, so we don't care, right? We don't care about the force for the retract. But if it has a load that's pushing back in both ways, extension and retract, then it does matter which one is more critical. If both are critical, then probably I should go to the bleed off. And that's why we have the bleed off. I think that's what you have on this slide. Okay, the area is the same. I mean, the area of the piston, your control is restricting the flow. blah, blah. The piston is greater, so that means the pushing during the extension would be limited. So if retraction is critical, then use meter N. If both are critical, then that's where we go for the bleed off. Okay. The calculation, it's the same, so I don't have any examples to solve for. And I think Brandon asked me that question, which, what problem was that, Brandon? I think it was the third one in the previous homework, which is calculating K. So he asked me what units, because in some notes they say when you calculate K for here, it should be in PSI per cubic inch, or the flow has to be in cubic inch per second. If you recall, delta P is K times Q squared. So P is in PSI, Q has to be in cubic inch per second. It's not a must, but what I need to mention here is just be careful for the units that you. This would be the square root of cubic inch per second, because it's delta P divided by Q squared. If you calculate K in this form, for a unit form, just make sure it remains the same throughout your calculation. We did solve some problems where you have a follow-up part where they would say, what happens if now the piston needs, the speed of the piston or the motor needs to be adjusted to half, to 10%, and so on. And you need to use that valve in part B. So if you calculate K in this unit, make sure you keep it in this unit, and you have Q in cubic inch per second in the second part. What you'll find in the solution of that homework is that I believe I had my K in PSI per square root of GPM. So if you have that question, what happens, like we need to calculate a new delta P or so to have the speed at 50%, then just make sure that whatever unit you calculate K, PSI per GPM, square root of GPM, use it the same, and you're going to get Q and GPM, or make sure you plug Q and GPM. Okay, we have two problems. Do read, I think I have some notes on Brightspace. Anyone check those? Assignment. Which homework is that? 3? Yes. Let me share this. Or let me share my screen. Screen. So don't solve from the text. I mean, probably you need to read the problems from the textbook, but make sure that you read those hints. Those are hints, so I don't think I changed anything from the problem. Here I did change this part from what you're supposed to do in the textbook. I said for part B, neglect the power loss due to leakage. Okay, so there'll be this, I don't know what it is, it a multiplication? Double check this equation. I can check it for you once we're done. I'm not sure what this symbol is. When I convert it to PDF uploaded, slightly different. But there is some leakage and there's power due to leakage. Neglect that, okay? If you read through the text, you might find an example and they're including that power in your in their solution. Okay. This would be due next Wednesday. It's not assigned yet, so I'll just make a new assignment. And then we're going to hit chapter 7. I'll just start with that. We still have, let me just do this.